So, good morning, all. I'm Dr. P. Sarala from Triple Department from MREC College, and I'm going to take the topic on electric potential from the electromagnetic fields. So, here let us start with the electromagnetic field. So, in previous classes, we have already dealt with what is Coulomb's law, what is electric field, what is force, what is a charge, and these type of topics are dealt previously already. So now I'm going to explain you about the electric potential. So what is mean by the potential, electric potential? So here the electric potential is nothing but the work done against the force. Okay, so here the potential is nothing but the voltage also. So let us go into the topic. So normally the electric potential. So suppose if we want to move a point charge, that is from a point A to point B. So in an electric field, from point A to point B, so some work is done in moving that charge from that point A to point B. And that is given by dW is equal to minus FdL. So here F is nothing but the force, dl is the distance traveled by that point charge. So here the force already we know in terms of electric field intensity, that charge into electric field intensity. So into dl. So here E is the electric field intensity we are mentioning here, and the negative sign is nothing but the work is done against the force. So it is done by some external agent. So here next, so same this one. So the total work. So let us go here. See here. This is a point A and this is the point B. So now we have to move the charge. So the charge has to be moved from A to B. So some energy is required in moving this charge from A to B. So the work done is nothing but, so here in this previous slide, we have seen that QE dot dl. So that is, it is a small distance traveled. So for let us take, this is the small length considered for work done. If you go for the total length to be considered, then we have to go for an integration. So we have to totally calculate the work done from moving a charge from point A to point B. So what is that? So W is work done is equal to work done or the potential energy. So here it is minus Q from A to B. So here we are integrating from the length we are calculating from A to B, E dot dl. So here the distance of point A from the origin, let us take RA, and the distance of point B from the origin, let us take RB. So if we consider there is a differential part on this length, then the distance of the differential part from the origin is, let us take the distance R. So now if we take the potential difference, so potential energy or potential difference, both are same. So potential difference between point A and point B is nothing but the total work done or potential by Q. So if we divide it, minus A to B E dot dl. So this is the total potential difference between the lengths A to B. So now in determining VAB is nothing but potential difference. A must be an initial point and B must be an final. If VAB is negative, now we have taken here, it's a negative value, right? So if VAB is negative, there is a loss in potential energy in moving a charge from A to B. Okay, so this implies that the work is done by the field. If VAB is positive, so let us take whatever the VAB formula is there, so this is positive. If we get the positive value, then VAB, there is a gain in potential energy in the moment. So that is that some work is done. So VAB is independent of the path taken. So it does not depend on the path, how the path is, whether it is in a circular shape, whether it is a line shape, whatever the path is. So VAB is independent of the path. So VAB is measured in joules per coulomb. Joules is the work done, work energy per coulomb. So now commonly we refer it to as V, volts. So now let us go with the some electric potential due to point charge. So we shall calculate an electric potential due to some point charge. Suppose a point charge is located at the origin. So let us go with a point. Let us go with the, suppose we are having a point charge. So point charge at the origin. So let us take three-dimensional one, and let us take the point charge is at origin. So now if we take the electric field intensity, that already we know, F by Q. So in previous classes we have studied, that is Q by 4 pi epsilon naught R square AR. So now VAB is nothing but RA, RB. So RA, RB. RA is the initial point, RB is the final point. So E dot DL. So normally what we referred, VAB is equal to, so what we learned here, minus A to B, previously we did, right? So E dot DL. So what is this DL? DL is in Cartesian coordinates. So this DL, so here we are taking AR. So directly we get AR dot DR dot AR. So it is, so Q by 4 pi epsilon naught R square AR dot DR AR. So now what we get? Q by 4 pi epsilon naught R square. R square is nothing but here 1 by RB minus 1 by RE. Why? Integration of 1 by R square. So what is this? Minus 1 by R. So if integrated, we get in this way form. Okay. So VAB is nothing but Q by 4 pi epsilon naught 1 by RB minus 1 by RA. So if we take the voltage VAB, that is the voltage at point B minus subtracted at voltage at point A. Voltage at point A. So here, now thus if VA is 0, let us go. Now we have calculated what we calculated here. VAB is equal to VB minus VA. Suppose if VA is 0, we are saying some assumptions are VA is 0. So then what it means that VA is 0? That one RA is tending to infinity. Because 1 by RA is, what is 1 by RA? If RA tends to infinity, it is 0. So if 1 by RA is 0, so VA is also 0. So the potential at any point RB tends to R due to point charge Q located at the origin is. So we are saying that VA is at far distance. VB is at origin, we are saying. Okay. So now moving a point. So already I said here. So if this point, let us take B point where the charge is located, and some at infinity. The A is at infinity value. A is at infinity. Then what is happening here? So we consider this distance as R, and moving a charge from point B to point A. E is given as VA equal to 0. So we take it as V is the potential difference, that is Q by 4 pi epsilon naught R. So this is the potential, electric potential due to the point charge. Now next come to another superposition principle. So these type of charges are meaning. Let us say these type of point charges are Q1, Q2, so on Qn located at points with position vectors R1, R2, Rn respectively. The potential at R is. So if we are going to have n number of point charges and we want to calculate the potential difference, then we have to use the superposition principle. So what is that? So if we are having the Q1 charge, R minus R1, Q2 charge, R minus R2, so on, Qn charge, R minus R. So let us take the potential 1 by 4 pi epsilon naught, K equal to 1 to N. So here, let us take, there are K number of point charges, Qk, R minus Rk. So these all potential, electric potential differences are sum of it. The total sum of the potential difference due to n point number of point charges are calculated by using superposition principle. So if suppose we are treating with respect to charge densities, if we are going with charge densities, so till now we have taken charges, that is Q1, Q2, Q3, Qn. If we want in charge densities, then 1 by 4 pi epsilon naught. So here, if we go with line charge, then we get rho L. If we go with surface charge, we get rho S. If we go with volume charge, we get rho. And also it is integrated with respect to line charge L, surface charge S, and the volume charge V. So here, if we go with in Cartesian coordinates, what is del V? Del V is nothing but dou V by dou X AX, dou plus A dou V by dou Y AY plus dou V by dou Z AZ in a Cartesian coordinates. If let us take this in cylindrical coordinates. So what happens in the cylindrical coordinates? Here we have to take into consideration rho, phi and Z. So rho, dou V by dou rho A rho, 1 by rho dou V, dou phi A phi, dou V by dou Z AZ. If we go with spherical coordinate system, then it is r, theta and phi. So dou V by dou r AR, 1 by r dou V by dou theta A theta, 1 by r sin theta dou V by dou phi A phi. So these are the different types of systems we are going to represent it. So now let us go with the relation between the electric field intensity and the voltage. So here, if we go with the potential difference between the points from A to B, the potential difference between the points A to B is independent of the path. Already I said it does not depend on the path which we take. So we can write VAB is equal to minus VBA or VBE is equal to minus VAB. So here, that is, if we add these two voltages, that is VAB plus VBA is equal to integration of E dot dl is equal to 0. So therefore, for a closed contour, the E dot dl is equal to 0. So for any closed surface, the E dot dl is 0. And if we apply the Stokes theorem for this formula, that is E dot dl, so this is line charge, and if we want to convert this into surface charge, then we have to take it as del cross E. E is converted into del cross E for the surface charge dot ds is equal to 0. So when we go with del cross E, then del cross E is equal to 0. So this is from the Stokes theorem. And now we go with a grad V. Grad V is nothing but del V. So dV is equal to minus E bar dot dl. Already we know. So what is E? E is nothing but in three directions, that is Ex, Ey, Az. So now if we take the dV, the potential difference, that is dV is equal to dV by dou V by dou X dx, dou V by dou Y dy, dou V by dou Z dz. So if we compare this dV value and this E value, then what is this dou V by dou X? Dou V by dou X is minus Ex. Dou V by dou Y is minus Ey. Dou V by dou Z is minus Ez. So now what we can write? We can write that E is equal to minus. So what is this dou by dou Y? Grad. We are representing this in terms of grad. So here dou by dou V it is V. So E is equal to minus grad V. So now next we go with another topic which is called as electric dipole. So what do you mean by a dipole? Dipole is nothing but the two quantities which are same magnitude but they are separated by a distance, same magnitude but separate different directions and separated by a distance. So here we can have dipole is nothing but two poles. Dipole, monopole is single pole. Dipole is two poles. So here we are representing with respect to electric dipole. So we have magnetic dipole too. So we have magnetic dipole and electric dipole. Now we are just seeing with electric dipole. So this electric dipole is nothing but in electric, what we consider charges. So dipole is nothing but two. So now two charges if we take of opposite directions. So that is plus Q minus Q. Okay. And they are separated by a distance, a small distance. It is not very large distance. It has to be separated by a small distance. Then we say that there exists an electric dipole. So here, see here, an electric dipole is formed when 2 point charges of equal magnitude but opposite sign and are separated by a small distance. So this is compulsory. They should be separated by a small distance, then only dipole exists. If they are separated by a large distance, that is one electric charge is at another place, another electric charge is at far away place. So we can't say that these two are existing dipoles. So must be having small distance between these two charges. Then only we say this as electric dipole. See here, this is the diagram. So here, now plus Q, positive charge, minus Q, negative charge. So now these are separated by a small distance D. And if we take any point charge in XY axis, then the distance of P from Q is R1. The distance of P from minus Q is R2. And the distance of P from origin is R. And now we calculate what it is. Okay. So now consider an electric dipole. The potential at point P is given. So now we have to calculate the potential at point P due to these charges. So that is Q by 4 pi epsilon naught 1 by R1 minus 1 by R2. Already we know how to calculate this potential. So Q by 4 pi epsilon R2 minus R1, R1, R2. So let us take this R is greater than this distance. So always you consider the distance from the origin of the point charge is greater than the distance between the two charges. So that is greater than D. And let us take R2 minus R1 approximately D cos theta. So if we consider a triangle 1, this one, a triangle based one, then we say that this R1 minus R2 is nothing but d cos theta, and R2 R1 are similarly equal to R square. We can say that R1 R2 multiplied is equal to R square. So now if we substitute it q by 4 pi epsilon naught R2 minus R1, what is that? D cos theta. What is this? R1 R2? It is R square. So since d cos theta is nothing but d dot AR, where d is nothing but dAz, if we define P is equal to QD, then we write that d cos theta is d dot AR. Now, after writing d dot AR, so here d cos theta is d dot AR. And what is this here? There is Q by 4 pi epsilon naught R square. And what is this QD here? We are writing P. QD is nothing but P. So that's why we are writing P dot AR 4 pi epsilon naught. So now let us go with what is this AR? AR is nothing but a unit vector of magnitude divided by some magnitude. So unit vector by magnitude. So what is that? R minus R dash. So now if we write AR as R minus R dash and also here R minus R dash, then we write it as this R square is also R minus R dash whole square, then again multiplied by R minus R dash, that is P dot R minus R dash. And here 4 pi epsilon not common. So what is this becomes square and 1, that is cube, and this is this one. So here if we take grad V, E is equal to minus del V. So that is equal to minus dou V by dou R AR plus 1 by R dou V by dou theta A theta. So we are considering cylindrical coordinates. So dou V by dou R AR QD cos theta 2 pi epsilon naught R cube AR QD sin theta by 2 pi 4 pi epsilon naught R cube. If we calculate this, we are going to get this values. Now E is equal to, so after this, we can write it instead of QD, we are writing P and we are taking 4 pi epsilon naught R cube as common. So here we get 2 cos theta AR plus sin theta A theta. So this is about the grad V. So here we stop the session. Thank you.